Okay, so now, since I know we're all ready, so class.
Yes.
Okay, all right. So let's pretend that we have been paying attention all this time because I've been doing my darndest to try and slow down as much as I can to make sure everyone is on track on this one. So, yes, are we still on track, caught up? So, the homework, and so we're gonna finish this up today, so that means homework will be due on Tuesday.
What?
Wednesday? Wednesday, right?
Wednesday. I thought it was 2 days.
Yeah, it's 2 days, so it's Wednesday, right?
Yep.
Okay, good, sorry. Okay, so making sure. So it's gonna be due on Wednesday, and if you have been keeping up with the homework to this point, it's not gonna be so bad. Tomorrow's gonna be a homework day, and then you guys are gonna be awesome. Alright, so a person standing at the end of a pier is docking a boat by pulling a rope at the rate of 2 meters per second. End of the rope is 3 meters above the water level. How fast is the boat approaching the base of the pier when 5 meters of rope are left to pull in? Assume the rope never sags and that the rope is attached to the boat at water level. Actually, there we go. So, this is 3 meters, right? 3 meters above the water. End of the rope is 3 meters above the water level. Pulling the rope 2 meters per second. And 5 meters of rope are left to pull in. So 5 meters of rope are left to pull in. So if my little dude right here, hold on, let me, there you go, my little dude. Okay, blue hair. And a hat. Okay, pulling in this boat, the rope is the piece that he's pulling, right? This is my rope, and that is going to end up being 5 meters at a certain time, right? And right here, how fast is the boat approaching the base of the pier? The boat approaching means it's going this way. Right? So if it's going in this way, then that means that I need to start giving some things some variables. This is going to be my x, this is going to be my y, and this is going to be my hypotenuse, which in this case I'm going to call it a z. Sometimes it could be a d because of distance formula, which is the same thing as Pythagorean theorem. So either way, it's going to work out. So I got an x, a y, and a z. Now, is the z changing? Because that's a rope, right? In this problem, we're pulling in the rope, right? Okay, good. So I could say that's going to be a dz dt, and in the problem, I believe it said 2 meters per second. Okay. What else do we know? What am I looking for? What's my end result supposed to be? is the end result supposed to be? What am I looking for in the end? Okay, how fast is it approaching? So which one is changing? Which one? Give me the letter. Very good. X. So yes, that's what I'm looking for, right? I want to know the rate that the X is changing. So that means that when the X is changing, that's going to give me a dx dt. That's what I'm looking for there. Is y changing? Y is not changing at all, is it? No matter when I pull it in, it's not changing. So let's set up my problem. So I'm going to set it up again with Pythagorean theorem. So I'm going to say x squared plus y squared equals z squared, or distance squared, whichever we want to try and use for it. Now, since we know y is not changing, that's going to be a constant right there, right? So that's going to be 3. All right, take the derivative. That's going to give me 2x dx dt plus 0 equals 2z dz dt. So let's look to see what I still need. I'm looking for dx dt. I gotta try and find what x is, right? So let's look. So if the y is 3, the z is 5, what's the x gonna be? Pythagorean triple there. 2. Not 2. Here, let's figure it out. Using that, 5, 3, 2, not 2. Right triangle, like this. So let's see. If this is my hypotenuse, that's going to be 5 squared plus x. Equals x squared plus 3 squared. My Pythagorean theorem, right? My hypotenuse is always this side. 25 is equal to x squared plus 9 minus 9. 16 is x squared. X equals plus or minus 4. But since this is the distance, what does it have to be? Can you have a negative distance? You cannot have a negative distance. So I got to make sure that my distance is positive. So that means x has to be 4. Okay, so now let's look. I know the x. I'm looking for dx dt. Do I know z? My z is 5, right? dz dt, do I know that one? 2 meters per second. So I could just plug those in now to see what I get. So two, 4 equals 2, 5 sake. There you go. Divide by 8. So dx dt is going to be, is it 5/2? And that's going to be meters per second, or 2.5 meters a second. Yes, no, maybe? Possibly. Carolyn? Yes? Good? Okay. Alright. Let's look at the next one. A revolving light located 5 kilometers from a straight line shore turns at a constant angular speed of 3 rad per minute. With what speed is the spot of the light moving along the shore when the beam makes an angle of 60 degrees with the shoreline? Now, these problems right here with the angles is kind of a pain in the butt. So, drawing it is always going to be the key. And then, this is my lighthouse. There we go. Okay. That's a lighthouse. Located 5 kilometers from a straight line shore. Okay. What else do I got? Turns at a constant rate of 3 rad per minute when the beam makes an angle of 60 degrees with the shoreline. So 60 degrees with the shoreline right there. There we go. So it should be set up now. Why did it do that? There you go. Give things variables. So this is my shoreline over here. So this is going to be my x, which is left and right, my y, up and down. Now I can start putting some information in. I know my theta is going to be that one over there, 60 degrees. My d theta dt is 3 rad per minute. And this is the part where reading the question carefully and drawing it carefully is going to help you. Because they kind of gave it to you as a false premise. They said your theta, your angle is 60 degrees with the shoreline, right? Is the shore moving though? My lighthouse over here is the piece that's moving, isn't it? So this angle over here is not the angle I need. That's not the angle I'm using here, because that's not the one turning. The one that's turning is going to be over here. So this one turning over here, if that's 90, that's 60, this one is 30 degrees. So that means this was incorrect. But if you draw it, you could actually see, oh, this is where my lighthouse is. The lighthouse light is turning. The shore is not the one that's turning. So angle right here is going to be 30 degrees when this one over here is 60. Now also, this information right here, my speed of my angle that's turning is 3 rad per minute. So that means that my units have to be what? Radian, right? Is 30 degrees radian? It's not, is it? So 30 degrees is not radian. What would 30 degrees be in radian? Pi over what?
6.
Yeah. Pi over 6. Okay, so now we're going to use some trig here. So this is my reference angle down here at the 30 degrees. Right? That one's 30 degrees. I need to find this one over here, x. Does y change? Is y going to have any change at all? Say no. No. Y is not going to change because that's the distance from the shore to the lighthouse. That's not moving. But x is moving, isn't it? X is moving. Okay? Speed of the spotlight moving along the shore. So that means I am looking for dx dt. So that has to be my end result. Now we're going to do a little bit of trig. If this is my reference angle, if that's my reference angle over here, the x would be considered my opposite, right? And what about this one over here? What is the y going to be? Adjacent. So opposite and adjacent. What ratio uses opposite and adjacent? Yeah, it's tangent, right? So it's tangent. So I'm going to have tangent of theta is equal to opposite, which is x, over adjacent, which is 5. I'm going to multiply both sides by 5 so I could actually simplify this a little bit. So 5 tan theta equals x. Now let's go ahead and take the derivative. You guys recall what's the derivative of tangent? Secant squared. So it's going to be 5 secant squared theta. Did I miss anything? D theta dt is equal to dx dt, because the derivative of x is just 1. Alright, let's see. Theta. We said theta is going to be pi over 6, right? Theta is pi over 6. So from my unit circle, I'm going to just use the first quadrant. Pi over 6 is right here. And x value is going to be rad 3 over 2. Now, secant compared to cosine is what? It's the reciprocal, right? So what would I do to actually just do that one right there? I would just take my rad 3 over 2 and flip it over, because that would be the secant. That would be reciprocal. So for secant, I'm going to go 5 parentheses 2 over rad 3, so that's a secant, squared times d theta dt 3. Do a little bit of math right there. What's that going to be? So that's going to be, what's that, 4 over 3? When I square that, 5 times 4 over 3 times 3 dx dt. So I get 20 is equal to dx dt. What are my units?
Radians per minute.
It's what?
Radians per minute. I'll add some meters.
It's going to be
Kilo.
kilometers, kilometers, right? So it's kilometers per minute. So if you think about this, the distance of 5 kilometers, since we're here in America, kilometers, 5K is like 3 miles. So 3 miles is a long way, right? So that would be the distance from Central down to like 16th Street, I think. I think that's where it actually breaks off. From Central, yeah. Central down to 16th Street is 3 miles. It's a pretty long distance, right? So as it's rotating, since it's really long, in a minute, it's going to go a very long distance way over there along 16th Street. So traveling at 20 kilometers per minute is actually pretty fast. Make sense? Oh, all right. So I think this was our last example that we have. Motion of circular angular speed W is defined as the rate of change of central angle theta of the circle with respect to time. That is, okay, that's important right here. This formula is going to be necessary. W is equal to d theta dt. That should be d theta over dt, where theta is measured in radians. There we go. All right, we are good. We're going to use the rest of the time for homeworks, and everyone's going to like, share, and subscribe. Right? Hit that notification button.